Yes, let's get. I don't know about you guys, but I feel like, the day after a test like that, class should be canceled. It's a shame that you have to come here and learn more math, but sadly, this is what you're paying for. You've paid your tuition dollars, and I'm here to entertain you with some math, as always. What's that? Learn to juggle instead. I don't think I'd be the right person to teach anyone to juggle. All right, well, it's 1:50. As always, the dream is that grades should be released hopefully Monday at some point. We've asked the TAs to try to have those all graded by Monday. I hope the exam went well for you, and we can talk about some more statistics or whatnot come Monday or Wednesday at the latest. But unfortunately, we need to kind of readjust and think about the next stuff. So this is now heading into Unit 2. This is the content that'll be on our midterm exam. And it largely covers Chapter 14 and a little bit of Chapter 16. So in Chapter 13, this was largely an upgrade of lines. So throughout all of Chapter 13, we were largely talking about vector functions, which were these space curves, right? So they mapped out some curve in space. And we did the calculus and we did some integrals and all that sort of stuff. In Chapter 14 here, we're going to be upgrading planes. So these are going to be general surfaces. So we'll talk about general surfaces. Chapter 14 will have us doing a bit of like calculus 1 stuff, mostly like derivatives and whatnot. We end Chapter 14 with finding mins and maxes and all that sort of stuff, but now in the multivariable case, so with x's and y's instead of just with x's. And then Chapter 15, we get a lot of the integration of surfaces. And so we'll have double and triple integrals and all that sort of stuff. So we'll be with surfaces for a little while here. But that's kind of a high-level overview of what Chapter 14 is going to be about. So in today's class, we have 14.1, which is basically all of the algebra of surfaces. So we're going to be talking about domains, ranges, and level curves. Those are the big 3 things that we need to talk about in 14.1. And then in 14.3, this is one of these rare days where we get 2 sections in one sort of deal. We start to get some of the derivative stuff. So we want to get to a bit of calculus in today's class, if at all possible. In the pre-class videos, we define domains and ranges. We give an example here, we sketch, and see, of course, right, this is the top half of a sphere. We talk about level curves. These kind of look like these, topographical maps sort of deal. And they give us the different heights. And then from those, we should be able to start to visualize a 3D surface with these labels here. So that's kind of what, again, the big 3 things for this section here, 14.1 are. So why don't we go ahead and maybe jump into the new stuff for today for 14.1. And then also there was a video on 14.3, which defined partial derivatives. I hope you had a chance to watch that. But if not, again, we'll do kind of a bit of an overview. Any questions on this pre-class video here before we jump into the new stuff? Yeah. So the question was, how do you know what the constant K is when you're doing level curves? So yeah, for quiz and exam problems, it's really best practices, right, if they specify what K values, right? If I say, and we'll see an example, which is fine here in, an in-person class sort of deal, or a class where, we can choose some various K values. But if it just says, graph level curves for various K values, you wonder, okay, well, how many do I need, right? Is 3 level curves okay? Should I do 4, right? And then also what K values does it want? Otherwise, everyone's picture is going to be a little bit different. Your picture may go off the page, right? Depending on what K values you choose. So yeah, it's really kind of best practice to provide the K values, especially for assessments. Yeah, but otherwise you can just take a sampling of them. Computers are, of course, very good at this too. Good. Any other questions? All right, well, let's do some algebra then. So this is going to be, again, bit of algebra, a bit of review here, but all just now in the multivariable case. So I want to remind us, when we have a two-variable function, this z equals f of xy, the domain is going to be a set of inputs. Now, because, right, we have two variables that we're inputting, we have an x and a y, this is really a set of xy points. These can be expressed in set notation, so we'll go over that. Curly braces and all that sort of stuff, or via graphs or a sketch in the xy plane. So you'll see a decent amount in the WebWork homework, right? If it wants you to do something with a domain, right, it'll probably give you some multiple choice. It'll give you several sketches of what it could look like, and you need to choose which one's the correct domain for the function given. On the other hand, when we talk about range, range is supposed to be an output, right? So in this case, we have the range, a set of z values. So the range is a set of z values. Those are numbers, right? So it's not an ordered pair, but they're numbers, things like 5 and 13 and negative 12 and what have you, right? And so therefore, these can maybe be most easily expressed using the interval notation. That again, hopefully you know and love from algebra notation. Forgotten. Hard to talk and write sometimes. All right, so we saw an example of these sorts of questions in the pre-class video. I have a couple more here. But ultimately, right, when we're trying to find domain, we are going back to our old algebra days, and there were three things really that we had issue with if you wanted to stay within the reals. The first is you shouldn't be dividing by 0. If you're dividing by 0, you don't get a real number. So anytime you divide by 0, that's not going to be in your domain. The second thing that you don't like is that you don't like to put negatives into square roots. This actually is true for all even roots. So 4th roots, 6th roots, go on, so on and so forth, right? You don't like to put negatives into even roots. And then once you get, and you know something about logarithms, right? You don't like to put negatives or 0 into logarithms. So these are the three things that kind of get you into the complex plane and whatnot. So these are the three things to really watch out for our class as well. And so starting off here, this is the function that I'm interested in sketching the domain of. Notice that I don't have any roots, no square roots, no 4th roots, anything like that. I don't have any logarithms, but I do have division, right? So the things that I have to be worried about are dividing by 0 in this case. And so I would divide by 0 if y minus x was equal to 0. That would be a problem. So I would like that not to happen. And if y minus x cubed was equal to 0, right? That's another place where I would be dividing by 0. So if either of those occur, that would be a problem. Everywhere else, we're fine. So everywhere else is going to be in the domain, but on those curves, the line and a curve here, right? That's what I take issue with. So let's go ahead and maybe sketch. And let's see, I don't want to be on, I guess I can rearrange this and make y should not be equal to x. And then, so y equals x would just be this nice straight line with slope 1 and intercept 0. I don't want it to be on there. So typically, right, if you don't want the line included, you do like dashes or something like this. So I did a dash line here. If you want the line to be included, you usually make it a solid line. And likewise, if I rearrange the other one here, we're going to get that y should not be equal to x cubed. So this looks kind of like a this classic cubic, something like that. So everywhere else is fine except for on those two curves. Maybe I'll cheat a little bit here. Should have white. Oops. There we go. So again, we shouldn't include those lines there, but everywhere else in the plane is perfectly fine. All right. So that's what the domain for this one looks like. if you wanted to express this in set notation, you would say the domain, maybe I'll call it D, is the set of points. And the first thing in set notation, you have to describe kind of what the points look like. So they, again, are going to be X, Y ordered pairs. And then you say straight up vertical line. This is usually stands for such that. And then you can write your conditions. So I would say that Y should not be equal to X. And Y should not be equal to X cubed. This is more the English and here for those of you, sticklers, it probably is better to say an or there. So Y should not be equal to X or Y should not be equal to X cubed. Either of those would be issues. So that's how you write it in the set notation. So I think the set notation is typically a little bit easier once you learn the syntax of it. It's a little bit maybe annoying to get used to where you need all the pieces, but once you do, right, it's not maybe as bad as having to sketch. All right, any questions on this one here? Yeah. Yeah, just to see it better. Yep. All right, let's try another one here, a little bit harder, and then see if you get any questions for this one. So on this one, again, kind of those three base rules that I was talking about, right? You really don't want to divide by 0. That would not keep you in the real numbers. You don't want to put negatives into square roots, and you don't want to put negatives or 0 into logarithms, right? And so, okay, we have a couple of things here. The first thing is that I have a place where I would be dividing by 0. If X was equal to 0, that should not be in my domain. And then the other thing that I see here is that I have a logarithm. So I want to make sure whatever I feed into that logarithm, that should not be negative and it should not be 0. So it must be positive. So in this case, that means that X squared plus Y squared minus 1, that's what I'm feeding into my logarithm. I want that to be positive. Otherwise, I'm not going to get a real answer out. So this one I can rearrange. I get X squared plus Y squared is greater than 1. So let's go ahead and again plot these things. X not equaling 0. So X is equal to 0 along the Y axis. So I really don't want it to be 0 there. So do a dashed line. And we also have here that X squared plus Y squared needs to be greater than 1. So if it was equal to 1, that means we would be on the circle of radius 1. But remember, we want it to be strictly greater than 1. So again, I'm going to be using a dashed line here just to indicate that we can go up to this line, but it shouldn't be included in our answer. And then we need to shade, right? So I'm going to certainly exclude shading in this line X equals 0. But then, right, I can either probably shade inside of the circle or outside of the circle. And one of those is going to correspond to when X squared plus Y squared is greater than 1. So what's your intuition there? Should I shade inside or outside? Outside. Okay, so it sounds like there's some good intuition. That's good. Let me go ahead and shade with a thicker pencil here. Something like this. And again, you're going up to, but not including this X equals 0 as well. Something like that. Now let's suppose that, right, maybe I don't have this good intuition about should I be shading inside of the circle or outside of the circle. Is there a way that I could verify, right, which one is correct? And the answer is yes, and you just need to choose a test point. So let me showcase that really quick. So I'm going to choose a test point that's outside of the circle, maybe over here. Let's see, that circle is a circle of radius 1. So let's suppose that this is the point 2, 0. And I'm going to plug that in to my inequality and see if it works out, see if it is a true statement or not. So if I plug this in, again, I'm trying to decide if I want to shade inside or outside of my circle. So that's why I'm using the circle one here. I would get 4 plus 0 is greater than 1. And yes, that is a true statement. So that indicates that I should be shading outside of the circle. Just for fun, we could also check inside of the circle and see if we should be shading there. So maybe if I choose the point here, this is 1/2, 0. And again, these are test points. You could really choose any point that you would like outside of the circle and inside of the circle. But I'll do 1/2, 0. And when I do that, I get what? 1/4 plus 0 should be greater than 1. And that's not true, right? That's just 1/4. That is not greater than 1. And so I should not be shading inside of the circle. So this is how we can just use some test points to figure out. Again, this one was maybe relatively nice, relatively straightforward. But if you have any where you are hesitant, which side of this line or this curve should I be shading, right? You can use test points for that. All right. Any questions on this one here? Oh, I should do the set notation. I forgot that. So let's go ahead. The domain, again, I'll call it D, is going to be a set of ordered pairs that have X values and Y values such that, and we want X to not be equal to 0, and we want X squared plus Y squared to be greater than 1. We want both of these things to be true in order for it to be in the domain. If either one of these is false, then it's not in the domain. Yeah. So again, yeah, X, well, no, because we do want both of those to be true. If either one of those is false, so for instance, if you were to plug in the point, maybe up here, 0, 5, this is outside of the circle, and yet it has the issue of being on that line, right? So the and statement is false there, right? So yeah, sorry, this should be and. Thank you for the correction. Happy with and there. Because yeah, you need both of those things to be true in order for it to be in the domain. Problem is that they're not equals, right? If they were like equals, then yeah, you would need or, but yeah, because they're unequal, that's why yeah. Capital lambda. I guess I'm not familiar with that. Yeah, that would be fine. So there are various ways, that you can denote the word and or. So I guess capital lambda is one of these. I know computer science has a bunch of these depending on the language and all that sort of stuff, and statements, or statements, all that sort of stuff. But I mean, I would say usually the most straightforward is just keeping it in English. Good. All right. Well, why don't we go ahead, and I'd like to do kind of a full problem here that has a bit of everything. We can do the domain. This should be relatively fast. Then I'd also like to tie it together with the range and talk a little bit about that, and then also level curves. So I want to kind of showcase all three of the pieces that we should be getting from 14.1 here. So again, looking at this, when we think about domains, the main issues are dividing by 0, plugging negatives into square roots and fourth roots and any even root, and then plugging 0 or negatives into logarithms. Those are the main things to watch out for. Well, I see here that I have a square root, so I want to ensure whatever I'm plugging into that is not negative, right? It can be 0, that's fine. And positive is nice too, right? But it shouldn't be negative. So again, we take whatever we're plugging in and making sure that that is greater than or equal to 0. We can rearrange here, and that would give us y is greater than or equal to x. And so then we can sketch. So in this case, y equaling x is fine. So I get this nice straight line here. We can go up to that and include it. And we're also supposed to have when y is greater than x. So again, maybe you have some good intuition about this. And you can go ahead and say, well, if y is greater than x, I want to make sure I get my big y values. My big y values are going to be up here. It's maybe a good way to think about it. But if you're at all hesitant about which side of the line you should be shading, right, go ahead and choose some test points. Right? You can choose when x is 5 and y is 0 off to the right here. Oops. And you could choose maybe 0, 5, right? You just choose a test point in each region and then see, right, which one gives a true statement when we plug it into our inequality. So again, set notation. Getting a little bit faster now. This is a relatively nice one. So it's just sets of XY points such that Y is greater than or equal to X. All right. Now we get into the range. So I think that in general, range style problems are maybe the most difficult of the three. And in fact, I did make a bonus video. It's in the set of pre-class videos, that playlist. So if you'd like to get I think it's another like 20 or 30 minutes of me just doing range problems. If you'd like to get some more practice with those, that's a good place to go to get more range problems. But let me try to illustrate what we do for these sort of range problems. The main thing that I like to do is think about kind of the outer function and then what we're plugging inside of it. And so let me say, so step number one, I would say is find range for outer function. And then step two, see if there are additional restrictions based on what you're inputting into it. I have tried to come up with the best instructions that I possibly can that are true for all problems. It's very hard to do so. I'm assuming that looking at this, you're not very happy. You don't quite understand what this is saying yet. After we do a few problems, I hope that you will. So we're going to look at the outermost function and think about what its range is, and then determine if we have to cut that down anymore, right? Based on what we're inputting into that. So for this problem here, we have the outermost function is we have a square root. So we have the square root of stuff. I'm going to use star, you could use u or whatever. But the outermost function is the square root function, right? And so this has a range of, and again, it is the positive square root function. So if you input 0, right, if the star there was a 0, square root of 0 is 0. So you can go up to 0 and include that. But otherwise, when you plug in things into the square root, you're going to get out positives, right? If I put in 100, the square root of 100 is 10. If I put in million, right, the square root would be 100, right? And so, right, as you plug in bigger and bigger things, it does go off to infinity. And we can think also about this kind of graphically, if you'd like, right? The square root of various things. We can output 0, and we can output the positives, and they do get larger and larger. It happens slowly, but you do get larger and larger, and it does go off to infinity there. So this is what I mean kind of by the step one here, is thinking about my outermost function and seeing what its range is. So now I know, right, looking at this, there's no way that I could possibly get negatives, right? However, right, in order to get all of these very positive values, I need to be able to plug in very, very positive things into this, right? So for instance, if I wanted my square root to output 1,000 or something like this, right, I'd have to be able to put in a very large number into that to take the square root, right? So in this case, what, 1,000, a few more of those. Yeah, so I need to input 1,000,000 in order to get out 1,000, for instance. So we need to check, well, can you actually do that? Maybe there are some additional restrictions based on the input here where you couldn't do that. So now I need to look at y minus x, the thing that I'm inputting into this, and see, right? I need to be able to get close to 0, and I need to be able to get close to infinity. Can I do that? And the answer is yes. So there aren't going to be any additional restrictions. So for instance, if I wanted to get very, very close to 0, I could input 0, 0. So it's going to give me 0. So I can successfully get out 0 from this thing. If I wanted to get 1,000, for instance, I could input 0 for x and my million for y, and I would get 1 million minus 0. That's going to be my square root of 1,000,000, which gives me the 1,000. So I can also get out my very large things. So the y minus x doesn't give us any additional restrictions. We can still put in basically all real numbers into my square root. And so therefore the range will stay as is. There are no additional restrictions. So my final answer for this one would be 0 to infinity. Let me showcase, though, an example here of a situation where the y minus x didn't give us any additional restrictions here. But let's think about maybe an alternative situation where the input would give us some additional restrictions. So for instance, maybe I had something like the square root of, let me make sure that I'm not copying another problem. Okay, good. So what if I did the square root of 25 minus x squared minus y squared? So in this case, after step 1, I would have still the outermost function is the square root function. So I'm thinking about its range, its set of outputs is from 0 to infinity. Does the inside, right, can I still get out all of those numbers, right? And in this case, I can get very, very close to 0. For instance, if I was to go ahead and plug in 5, 0, so 5 for x and 0 for y, I would get the square root of 25 minus 25, so that equals 0. So yes, I can get very, very close to 0. But my claim is no matter how hard you try, you cannot get 1,000 in this case, right? Last time I had to plug in x equals 1,000,000, sorry, y equals 1,000,000 and x was 0, right? And I could get very big numbers. What's the biggest number you could ever input into the square root here? Anyone see that? So that would be the biggest output. So the input, right, the largest thing that you could ever have inside of the square root here is going to be 25. And that happens when x is 0 and y is 0, right? Because otherwise you're subtracting some stuff away. And so once you start subtracting away, right, because these are squares, these are positives, right? That means that the largest output that you're ever going to get is the square root of 25. So in this case, we have this additional restriction, and the answer here would be, right, the smallest thing you can get out is 0. That stays the same. But the largest thing that you can get out is going to be 5, the square root of 25. So that's how the inside bit can somehow influence this. Right, so you do have to check and make sure that kind of you can get a broad range of values. If there's something that's kind of limiting, in this case, right, I can never plug in anything larger than 25, then that's going to reduce your range. So it's no longer 0 to infinity, it's now 0 to 5. All right. Again, we'll have our next problem down here is also a range problem to get a little bit more practice with this, but I made a long video about ranges, which I invite you to watch as well. All right. So C is sketch some level curves, and then D, try to sketch the graph from those level curves. So sketching some level curves, we know that the range of outputs, the various K values, should be positive, right? So I could go ahead and choose, for instance, maybe like K equals 0. We could do 1, 2. That's probably enough. So we'll do 3 in this case. See what those looks like, and then try to sketch the graph based on those. So level curves, these K values, these are our outputs. So maybe when K equals 0, my first one here, if I wanted my function, the square root of y minus x, to output 0, the question is, where am I in the xy plane, right? And so, okay, well, I could square both sides, and I could rearrange. Usually I like rearranging and getting a y equals if possible. Seem to be pretty good at graphing those. And I get y equals x. So all along the straight line here, slope 1, intercept 0, the output, right, the height of the function would be 0. So that's one of the level curves. Let's do another one, maybe when k equals 1. I want to know all the places that give me out a height of 1 on the surface. So again, I'm going to go ahead and take my function, set it equal to 1 in this case. So I want the output 1. And we could go ahead and rearrange and try to get a y equals. Those are pretty nice to graph. So let's see, y minus x is equal to 1 after I square both sides. Y is equal to 1 plus x. So this is going to be a line with slope 1, but now the intercept's up at 1. So up here. These are all the places that the surface would have a height of 1. And then finally, why don't we do a height of 2? So I want my function here to output the value 2. So y minus x is equal to 4 after I square both sides. So y is equal to 4 plus x. So now I have up here 1, 2, 3, 4. So it seems like we're getting larger outputs if we go up and to the left, although they do seem to be taking longer to get to them. So if I want to go ahead and try to graph this now in 3-dimensional space, remember I have my positive x and my positive y here. So I would like my height 0 curve, so that's going to be right in the xy plane, to go right through the origin, just like I did over here. For height 1, it looks like I need to go up by 1 in the y direction. And again, it's supposed to be at height 1, so it's going to be up here at a z value of 1. So otherwise, let me go ahead and maybe draw a line first, and I'm going to move it to its right spot, using technology a little bit. Point here. And I want to make sure that it's going through, right? Again, the y value should be 1 here, but it should be at a height of 1. So the z value should be 1 as well. And then finally, one more, we need to go up to a y value of 4. And then the height, the z value, right? This is all the places where the surface has a height of 2, a z value of 2. So again, let me kind of cheat off to the side here really quick. Do my best to move this into place. That doesn't look super parallel, but something like that. And so if you were to use like a 3D plotter or whatnot, what you would see is that you get the square root function. You know, the square root function, as we have back here, it kind of looks like a, again, inverted parabola or a sort of wave here. And you get the same thing, but it's going off into this top left corner, right? So towards the positive y's and negative x's. So this right here is what the surface looks like. And again, it goes on forever here. And so again, the square root kind of is heading off to the top left if we were to look in just the XY stuff. So those are the different heights. If you wanted to know where it's 3, it's going to be even farther top left. All right, so that's a kind of the full picture, the full kind of 3 skills that you need from 14.1. Again, domains, ranges, and level curves. Any questions? Yeah.
So our k value is like c value?
Yes. Yep. The k values are various outputs. Usually, right, if we're talking about the full function, right, we usually say that this is z equals. So the k values are z values. That is a true statement. Yep. Good. Any other questions? All right, well, I'd like you guys to try, maybe for 60 seconds or so, and then see if you can figure out the range for this function here. And if you want a hint, you could maybe first by trying to find the range of just the 2 to the x times y bit, and then worry about the plus 3 later. All right, let's start talking about this one together here. So if you wanted to, you could say, right, and start with the full function, right, that this has 3 plus 2 to some power, right? That's kind of the outermost thing that's happening here. But my hint to you is maybe just start with a 2 raised to some power. I think that's maybe a little bit more natural, and think about what that range is. So that's what I would like to take as my outer function. And then we need to deal with what we're inputting into that and figure out, are there any additional restrictions based on that input? So, okay, first off, if I was to just deal with maybe this nicer case here, 2 raised to some power, what is the range of 2 raised to some power? Yeah, in the back here. 0 to infinity. You want 0 to be included or not?
Sorry, 1, 2.
You're getting farther away. I started to question you and ruin things, but yeah, so 0 to infinity, I like. Exponentials in general look like this. They have a horizontal asymptote at 0, so they get very, very close to 0, but you can't actually reach 0. This is true for e to the x, right, which is maybe the most classic, the natural exponential, 2 to the x, 3 to the x, whatever you want, right? When you take something, you raise it to powers, right? You get very large numbers if you go off to the right, and you get very small numbers close to 0 if you go off to the left in this case. So if I wanted to instead solve this other problem over here, that plus 3 is just going to take that same picture here, but then raise it up by 3. Right? So we're going to, instead of my horizontal asymptote being at 0, my horizontal asymptote is at 3. So that means that so far, right, if I wanted to include back that 3 there, that my range is going to be 3 and larger. So the next step is that I need to think about my restriction, right? What am I inputting into this? Are there any additional restrictions based on that? So notice that in order to get out the very, very positives, the very, very large numbers, I need to be able to put in to this thing something off to the right quite a lot, right? I need to be able to plug in a very large positive number. So can I make x times y very large and positive? I think so, right? I could give you a challenge, right? If I wanted to input like 1 million into this thing, could you figure out an XY combination where x times y is 1 million? Yeah, right? You could do 1 million times 1, for instance. That would be perfectly reasonable. So yeah, I think I can go as far off to the right as I want. If I wanted 1 trillion, I could do 1 trillion times 1, right? Can I go far off to the left? Can I make this very large but negatively large, right? Can I plug in stuff way off to the left here towards my asymptote? Well, let's say if I wanted to plug in negative 1 million, could you figure out an XY combination that gives me negative 1 million? Yeah, right? Again, we could let one of them be 1, and then the other one be whatever you want it to be, right? You can negative 1 million, fine. 1 times negative 1 million. You want a negative 1 trillion, fine, right? So yes, I think I can go far off to the left and far off to the right, right? And so therefore I should be able to get this full range. And so the second step here, oops, x times y has no additional restrictions. So the full answer is going to be from 3 to infinity. These ones are a bit difficult to ever show up as a standard response style question, right? Kind of the work that you show is a lot more reasoning with yourself rather than writing down specific steps or anything like that. Every function seems to be a little bit different. And so these show up fine as multiple choice or true false style questions, but not so much as standard response. If it is standard response and we're giving partial credit, usually it's just based off, you get so many points if the left endpoint is correct, so many points if the right endpoint is correct. And you get points maybe if it's parentheses versus brackets sort of deal. It's really hard to showcase work for some things like this. All right, any questions on this problem here? All right, well, in the interest of time, let's do this one really quick all together, and then we need to talk a little bit about 14.3. So which of the following best describes level curves of this function? And so we have a multiple choice style question, and this is what we're trying to answer. So again, level curves, various k values. And I could think about, I could plug in some specific ones. So for instance, if I wanted to do like the last time when k equals 0 or k equals 1, maybe that should be enough to give us an idea of what the answer is in this case. So if I have 0 is equal to e to the x plus y, well, just like 2 raised to some power can never be 0, it can be very close to 0, but it has an asymptote at 0. That means that we're not going to get a picture here. So if you wanted to try to solve for this, right, the next step is to take the natural log of both sides. That's going to cancel your e, but the natural log of 0 is undefined, right? Your calculator will remind you of this. Natural logs, they don't like negatives and they don't like 0. So this one, you don't get any picture. So, okay, since we didn't get a picture there, maybe let's add in k equals 2 as well. When I do 1, and this one I stand a chance with. I can take the natural log of both sides. Oops. Natural log of e is just whatever's on the inside, in this case, x plus y. The natural log of 1 is 0. So this means I have 0 is equal to x plus y, or that's going to be y is equal to negative x. So of course I could sketch this, but I know that this is going to be a line, right? Doesn't tell me that I have to sketch it in this case, but this is a line. The slope is -1, the intercept 0. Let's do one more, because I think maybe in general there'll be lines, but it's good to get a couple of these just to be sure. So 2 for my output. natural log of 2. Again, applying a natural log to both sides to cancel out that e. And then we're going to have negative x plus the natural log of 2. So this one has an intercept, right? The natural log of 2, you could plug that into our calculators to kind of remind us what it is. It's somewhere between 0 and 1 here, but it's just a number. So again, this is going to be a line. So we have line here, we have a line here. And so, yeah, I think overall, these things are going to be lines. So that's a good way to solve a problem like this. All right, so 14.1, I'm happy with the amount of time that we spent on 14.1 in this class here because I think that's the difficult stuff. 14.3 we need to talk about next, which I'll bring up the pre-class videos, but we get a lot of practice with partial derivatives kind of for the rest of the chapter. And so we will get more and more time with these things. So I'm not upset about kind of the time here. So in the pre-class video, I talked about how, again, there is a limit definition. Ultimately, when we do these derivatives, you can use the good old classic rules that you know from Calculus 1, the chain rule, the product rule, the quotient rule, all that sort of stuff. But you just have to get kind of good at holding whatever variable you're not taking the derivative with respect to as a constant. So you're not going to be using, right, this isn't implicit differentiation or anything like that anymore. It's holding one of the variables constant and thinking of it as a constant along for the ride, right? And the other one is what you're taking the derivative of. So for instance, for this first one here, when I took the derivative of x squared times y, and again, we were taking a derivative with respect to x at this point, that y I treat just like it's a 3 or a 5, right? It's some constant. I don't know what it is, but it's some constant. And so notice that when I took the derivative of this, I didn't use the product rule, right? If I wouldn't use the product rule when I had, 3 times x squared, and so I'm not going to use the product rule here. And so when I take the derivative, well, the derivative of x squared is just 2x, and y is along for the ride. It's some constant. And so it takes a little bit of adjustment, getting your eyes kind of used to this. But yeah, that's the strategy for when we take these partial derivatives here. There are various notations. The subscript notation is kind of, I would say, my favorite, but you can also use the partial notation. This is more akin to the Leibniz notation from Calculus 1. And I'll say the big theorem that we got in this section here is Clairaut's theorem. And it says if you have a nice function, so it needs to be continuous and defined and whatnot. So, the second partial derivative should be continuous and defined around this point. Then it doesn't matter the order in which you take partial derivatives. So you can do x first and then y, or you can do y first and then x, and they will output the same result. So long as you have a nice function, that's the case. Okay, so my goal is to maybe start with getting some more practice taking derivatives here. Before I do that, any questions about that quick overview of the pre-class video, 14.3? Okay, so let's try to do at least this one here. So I would like to take a partial derivative of my function with respect to x. So that's the subscript with the single x. Then we're going to do it again. So this is 2 derivatives, both with respect to x, right in a row. And then this one is a derivative with respect to x first and then y. So let's go ahead and start off with taking our partial derivative of our function here with respect to x. So now notice I do have a quotient. And in both the numerator and the denominator, I have x's. So I truly do need to use the quotient rule in this case. So the quotient rule says I need to take the derivative of the top. So the derivative of x times y is going to be 1 times y times the bottom minus the top times the derivative of the bottom. And again, I'm taking a derivative with respect to x. So the derivative of x is 1 and the derivative of a constant, y is a constant with respect to x, is going to be 0. Divide that by the bottom squared. So that's my good old quotient rule back from calculus 1. But again, we're treating y as a constant here because we're taking a derivative with respect to x. So it's just along for the ride. You can quite literally, if you wanted to, if it helps your mind a little bit, you can put 3s, right? And you could quite literally take the derivative of this and then swap back in everywhere you saw a 3, you could put a y. It's literally you're just treating it as a constant, some constant. And so it's just along for the ride here. So why don't we go ahead and simplify a little bit, just because we're going to have to take the derivative of this thing next. So if I distribute here, I'm going to have xy minus y squared, and then minus xy times 1, I suppose. So a little bit of cancellation. And so my final answer is negative y squared on top, x minus y squared on bottom. What about the other y? I distributed that one. All right, so I do see it's 2:40. I want to be respectful of your guys' time and everything. So this is where I will stop. If you take the derivative of this function now with respect to x, you get our second answer. If you take the derivative of that with respect to y, you're going to get our v sub xy. And so you can do those as well. Just as always, I'll post the solutions to this on D2L, hopefully by 4 o'clock today. So please do, try to fill this out, and then you can see the results. So I'll stick around if there are any one-on-one questions. Otherwise, I hope you guys have a great weekend, and I'll see you on Monday. We'll continue doing more partial derivatives and doing some tangent planes rather than tangent lines. So, all right, see you then. Second here.